In this toolkit, we look at some more information and some more examples of systems that we would solve using the y1 equals y2 method. Looking back at that toolkit, y1 equals y2, the big idea here was that we have two equations equal to y, and since at the solution to the system, those two y's are equal, we can set both equations equal to each other. Sometimes this is not directly possible because we don't have y isolated by itself on one side of the equal sign. So we may need to do some transformation to make that happen. This one does already have y isolated, but this one does not, so I need one simple transformation. Adding 2x to both sides, now I have y isolated by itself on one side of the equal sign. So y equals 2x minus 6. I basically just moved that 2x over using inverse operations. Now, this y and this y are equal to each other at the solution. So I can set those two equations equal to each other. I can say negative 5x plus 1 equals 2x minus 6. And hopefully you have more room than this when you're writing yourself. Solving this equation, adding 5x to both sides, I have 1 equals 7x minus 6. Adding 6, 7 equals 7x. And that gives me 1/2 to my solution. My x value is 1. I now just need to plug that back in to find my y value. Y equals negative 5 times 1 plus 1, which is negative 5 plus 1, which is just negative 4. That gives me my entire solution to the system, which is x equals 1, y equals negative 4. I don't have room on here to check using the second equation, but I can do that mentally. Does y, negative 4 minus 2 times 1, does negative 4 minus 2 equal negative 6? Yep, negative 6 equals negative 6. I would highly suggest that you always at least check in your head. So I can even go back and check this one. Does negative 4 equal negative 5 times 1 plus 1? Does negative 4 equal negative 5 plus 1? Yep, negative 4 equals negative 4. So we want to ensure, at least mentally, that our ordered pair is a solution to the system by plugging it into both equations. Something that we should point out is this doesn't just work if we have two equations with y isolated on one side. If we have two equations written as x equals, we know that the x values are equal at the solution. So I can use the same strategy, and I guess I would call it x1 equals x2. And I'm just going to now set these two right-hand sides equal to each other. So now I have negative 3y minus 6 equals 2y plus 9. Now I'm solving for y first instead of x. Hopefully you find this equation to be so easy that you don't need to even be able to read my handwriting. So I added 3y. If I'm reading my handwriting right, that gives me negative 6 equals 5y plus 9. Subtracting 9, negative 15 equals 5y. That gives me, oh, I did the thing Miss Courtney does not like. I switched y in my head, so I should have written here negative 3 equals y, and then y equals negative 3. Here's where I need to really start being careful about how I write my ordered pair. It's really common for students, the first variable that they solve for, they write that first in the ordered pair. Nope, I have y now, so I need to write that as the second part of my ordered pair. Now I need to find x. X is found by multiplying y by negative 3, so negative 3 times negative 3 minus 6, 9 minus 6, which is 3. So 3 is my x, negative 3 is my y, and of course I want to check with the second equation to ensure that I'm correct. Does 3 equal 2 times negative 3 plus 9? Does 3 equal negative 6 plus 9? Yep, 3 equals 3. And I like to even check that first equation that I just used. Does 3 equal negative 3 times negative 3 minus 6? Does 3 equal 9 minus 6? Yep, 3 equals 3. Okay, so y1 equals y2 could really be called, well, it includes x1 equals x2.